Welcome to the deep dive. Today, we're tackling Fowler Nordheim tunneling.
Fowler Nordheim, yeah.
Now, if that sounds like something, stuck in a physics textbook, think again. This seemingly obscure quantum phenomenon is actually, well, it's kind of the unsung hero powering a huge amount of the technology you probably rely on every single day.
That's absolutely right. At its core, Fowler Nordheim, or FN tunneling as we often call it, is the really fascinating quirk of quantum mechanics.
Okay.
Imagine an electron facing an energy barrier. Classically, it shouldn't have enough juice to get over it.
Right, like a wall.
Exactly. But with FN tunneling, if you apply a strong enough electric field, it's almost as if that barrier gets momentarily thinner, allowing the electron to just sort of pass right through, tunnel through.
Wow. Okay, exactly. And to really get to grips with this, we've pulled together a great set of resources.
Yeah, looks like a good mix.
We've got everything from detailed scientific papers, some book chapters, even some more accessible encyclopedia entries.
Good. A broad view.
So our mission in this deep dive is really to unpack this FN tunneling, show its critical role in modern electronics, and maybe highlight some of the truly remarkable ways it's being used.
Sounds like a plan.
So where should we start? Where does this tunneling first really show up for most people?
I think a logical starting point is something you almost certainly have nearby, maybe even in your pocket right now.
Digital memories.
Memory, like...
We're talking about flash memory, the kind you find in your phone, your laptop, solid-state drive, those USB sticks.
Right, okay. Flash memory. So how does this weird tunneling trick let us store, all our photos and data and everything?
Well, in flash memory, FN tunneling is basically the workhorse for writing information. They call the process programming.
Programming. Okay.
So to store a zero in a memory cell, you need to get electrons onto this special thing called a floating gate.
A floating gate?
Yeah, picture it like a tiny isolated island that can hold an electrical charge.
And getting electrons onto that island, that happens thanks to FN tunneling when you apply pretty high voltage. One source mentioned around 18 volts.
18 volts? That sounds like a lot inside a chip.
It is, relatively speaking. But that strong electric field is what dramatically sort of squeezes or thins the insulating barrier around that floating gate, making it just thin enough for electrons to tunnel through onto the island.
Okay, so a big jolt of voltage creates this, temporary quantum shortcut through the wall.
Exactly, a shortcut.
And electrons hop onto this isolated island, and that represents a zero. Got it. Now, what about changing it back, getting a 1? That's the erase operation, right?
Precisely. Erasing in flash memory also uses FN tunneling, but kind of in reverse. Here, you apply a large negative voltage.
Right.
One source talked about grounding the control gate and hitting the substrate underneath with maybe 20 volts.
Right.
This effectively yanks the electrons off the floating gate back through that same thin barrier, resetting the cell to a 1.
Pulling them back out. Okay. And you mentioned something interesting about erasing. It's not cell by cell.
Yeah, that's a key difference. Erasing usually happens on a block-by-block basis. You clear out whole chunks at once, unlike programming, which can often target individual cells or smaller groups.
Block by block. So clearing out sections of memory altogether. Now, I also remember reading that these different actions, reading, programming, erasing, they don't all happen at the same speed, do they?
No, not at all.
Yeah.
And that's a key point with real-world implications for, how snappy your devices feel.
Right.
For instance, one source cited a Micron 8GB flash chip reading data super fast, maybe 25 microseconds.
Okay, tiny fraction of a second.
Yeah. Programming, writing that zero, takes a bit longer, around 220 microseconds in that example.
Still pretty quick, but noticeably slower.
Definitely. But then erasing, that's the real slowpoke. It took 1,500 microseconds or 1.5 milliseconds.
Wow, that's way longer. Why so slow for erasing?
Well, think about it. You need to apply that strong reverse field across a whole block of cells and effectively pull out all the accumulated charge. It's just a more cumbersome process electronically to ensure all those cells in the block are properly reset. It highlights a fundamental trade-off, really, in how we manipulate these quantum events at scale.
Right, physics constraints. Okay, wow, a pretty significant difference then. Now, flash memory isn't the only type of non-volatile memory, the kind that remembers stuff even when the power's off, is it? I recall hearing about EEPROM.
You're absolutely right. EEPROM, that stands for Electrically Erasable Programmable Read-Only Memory.
Catchy name.
Yeah. It's another type. And it uses a related tunneling mechanism, sometimes specifically called Nordheim-Fowler tunneling, or NFT. Basically the same physics principle.
Okay, related. What's the big difference compared to flash?
Well, a key difference is that EEPROM can usually be written to and erased electrically at a much finer level, down to a single byte.
A single byte. Wow, that's much more precise than erasing whole blocks like in flash.
Exactly. Much more granular control.
So where would we typically find EEPROM being used?
Because of that byte-level flexibility, it's really useful for storing small, individual bits of data that might need occasional updates. Think about maybe your car's seat memory settings or the basic configuration data in your smart TV or washing machine.
Ah, okay. Little settings here and there.
Yeah, stuff that doesn't change constantly but needs to stick around. Like flash, it's non-volatile because the charge stays trapped.
But you said it's byte addressable. Does that come with any downsides?
Well, sometimes the structures in EEPROM, maybe the tunnel oxide layer, can be even thinner or stressed differently, which can mean they sometimes have a more limited lifespan in terms of how many times they can be erased and rewritten before wearing out.
Ah, wear and tear.
Exactly.
Right.
Manufacturers usually specify a minimum number of guaranteed erase write cycles. Maybe 100,000 or 1,000,000 cycles, depending on the type.
That makes sense. It's always about finding the right tool, the right balance for the specific job. Okay. Now, the sources also got into some really cutting-edge stuff, using silicon nanowires in memory. That sounds incredibly tiny.
It really is. Researchers are pushing the boundaries with silicon nanowire, or SiNW-based memory, often in a structure called SONOS.
SONOS, like the speaker.
No, different SONOS.
Yeah.
It stands for silicon oxide, nitride, oxide silicons, all about the layers.
Ah, okay. Layers.
Yeah, this layered structure is crucial for controlling the electric fields needed for that FN tunneling we talked about.
Right.
And what's really fascinating is how the incredibly small size of these silicon nanowires, we're talking diameters, often around, say, 20 nanometers, can significantly boost performance.
How does being smaller help?
Well, the tiny geometry, especially if it's a sharp wire shape, acts like a lightning rod, basically. It concentrates the electric field right in the crucial tunneling region.
Focuses the field.
Exactly. Making it easier for those electrons to punch through the barrier, even with potentially lower overall voltages or faster pulses.
So tinier wires could mean faster writing and erasing because the field gets more intense right where you need it.
That's the idea.
Yeah.
For you, the listener, this miniaturization at the nanoscale could eventually mean, even faster saving of photos and videos on future devices.
Very cool.
Yeah, the probability of tunneling goes up exponentially with the electric field strength. So small changes in geometry can have a big impact. And these scaled-down nanowire devices, they've even shown potential to store 2 bits per cell.
Wait, 2 bits in one tiny cell. How?
Think of it like having 2 separate little buckets for electrons within that single memory cell structure. By controlling the voltages precisely, you can fill one bucket or the other, or both or neither. For states, that's 2 bits of information.
Doubling the storage density.
Exactly. Huge for making memory smaller and cheaper in the future.
That's amazing. Okay, the sources also mentioned swapping out that nitride layer in SONOS, using silicon nanocrystals instead. What's the benefit there?
Right. Silicon nanocrystals, or SiNCs. They can act as more isolated, discrete traps for the electrons compared to a continuous nitride layer.
Okay, like little islands within the insulator.
Kinda, yeah. They have a slightly different energy structure that can lead to better charge confinement, less leakage.
And what does that mean practically?
Importantly, it can mean significantly improved data retention, how long the memory holds on to its state, especially when things get hot. One study we look at showed basically no loss of stored data at 85 degrees Celsius.
Wow, that's pretty warm.
Yeah, like inside a running computer or a car dashboard on a sunny day. No loss over long periods in these SiNC devices. That's a real advantage for reliability in tough conditions.
So better data security, better reliability, even when things heat up. That is a big deal. Okay, and then there was this term, junctionless, SiNW, SONOS. What's the idea behind making it junctionless? Sounds simpler.
It potentially is, from a manufacturing standpoint. Traditional silicon nanowire transistors, which form the basis of memory cells, often involve creating specific doped regions, junctions within the wire, to define the source and drain.
Right, the start and end points for current.
Exactly. The junctionless approach tries to get rid of those tricky-to-make junctions. The idea is to simplify the fabrication process, which could make building these advanced 3D memory structures more cost-effective down the line.
Simpler manufacturing. That makes sense for something you want to make billions of.
Precisely. In these devices, the entire nanowire, which is uniformly doped, essentially acts as the channel, and you control the current flow entirely with the surrounding gate electrode.
Okay, simpler to make. But does it perform as well? How does it stack up?
Interestingly, yes, they can perform comparably. The way the current flows is a bit different, more like bulk conduction that gets pinched off, but you can still get good memory characteristics. The key seems to be the doping level, how many impurity atoms you add to the silicon.
Ah, the doping. How does that affect things?
Well, higher doping generally speeds up the writing, the programming process. More electrons are readily available, and the field effects can be stronger near the surface.
Faster writing with more doping.
Okay. But lower doping can sometimes speed up the erasing process, so there's a trade-off.
A balancing act.
Always.
Oh, right.
And intriguingly, higher doping also seems to lead to more reliable charge storage in these junctionless devices, better retention. So engineers have this dial, this doping concentration. They can tune to optimize the memory for different needs, speed versus retention maybe.
So they can fine-tune the silicon itself to get the best overall results? Clever. And the sources even described a way to store 2 bits in one of these junctionless vertical SiNW cells, right? That sounds like stacking tricks on top of tricks.
It really is. By using a vertical nanowire, standing upright, they can carefully control where the charge gets trapped along its length. Maybe closer to the top connection or closer to the bottom substrate.
2 different locations on the same wire?
Exactly. And by trapping charge preferentially in one location or the other, they can effectively store 2 independent bits.
How do they control where it goes?
They use different voltage pulse schemes for writing and erasing. One source mentioned using FN tunneling for the erase, but a different mechanism called band-to-band hot hole injection, or BTBHHI, for programming distinct locations.
Wow, BTBHHI. Another mechanism.
Yeah, it involves creating electron hole pairs and injecting the holes. It's complex, but it allows spatial control. And then they use a clever reading method, maybe reading the current from different directions, to figure out which bits are stored.
That's incredibly ingenious. Seriously feels like they're constantly finding new ways to cram more data into smaller and smaller spaces.
That's the name of the game in memory technology.
Okay, now the sources also briefly compared vertical versus lateral silicon nanowire memory. Building them up versus building them across the chip surface. What are the main trade-offs there?
Right. Well, both vertical and lateral SiNW designs generally offer big advantages over the old, flat, planar memory cells, mostly because the gate electrode can wrap around the wire, giving much better control over the electric fields. Better gate control.
Okay, both are better than flat.
Yes. Now, lateral nanowires, the ones lying flat, especially when you can make them incredibly thin, we saw examples down to just 5 nanometers.
5 nanometers, that's insanely small.
It is. Those can achieve really, really fast writing and racing speeds because the field enhancement is huge.
Super fast lateral ones? What about vertical?
Building really thin vertical nanowires consistently can be more of a manufacturing challenge. So their speed boost, while still good, might not always be quite as dramatic as the absolute best, thinnest lateral designs.
Okay, maybe not quite as fast.
Maybe not. But the huge advantage, the big win for vertical nanowires, is their natural ability to be stacked upwards. You can build layers upon layers. Think of creating multi-story buildings, but for memory cells.
3D stacking.
Exactly. This makes vertical SiNW structures a very, very promising path for achieving extremely high memory densities in the future, packing way more bits into the same chip area, even if the absolute speed gains aren't always the record breakers compared to the most aggressively scaled lateral wires.
Density versus raw speed, potentially.
Right. And there was even a proposal mentioned for stacking multiple memory cells along each vertical nanowire, creating a true 3D multi-level memory array.
It's like microscopic skyscrapers full of data.
Yeah.
Absolutely mind-blowing. Okay, now, before we completely leave the world of memory, there was one more quick mention. Ferroelectric tunnel junctions, FTJs. Does our friend FN tunneling pop up there too?
It can, yes. Ferroelectric tunnel junctions, or FTJs, are another really exciting area for non-volatile memory. Different principle again.
Okay.
These devices have a very thin layer of a special material, a ferroelectric, sandwiched between 2 electrodes.
Ferroelectric, meaning?
Meaning its internal electrical polarization, like tiny built-in electric dipoles, can be flipped back and forth by applying an external voltage.
Okay, flippable internal charge.
Right. And this change in polarization directly affects how easily electrons can tunnel through that thin ferroelectric barrier. It changes the barrier height or shape. This is called the tunneling electroresistance effect, or TER.
Ah, resistance changes based on the ferroelectric state?
Exactly. Now, at lower voltages, often it's direct tunneling, where electrons go straight through the barrier. But especially when you apply higher voltages to switch the ferroelectric state or read it strongly. FN tunneling can kick in and become a significant or even dominant part of the current flow.
So FN tunneling joins the party at higher voltages in FTJs, too.
It can, yeah. Researchers are even exploring how the switch between direct tunneling and Fowler Nordheim tunneling, triggered by the ferroelectric polarization change, could lead to very large changes in resistance, a huge difference between the on and off states, which is obviously great for memory.
Okay, so this fundamental tunneling idea just keeps appearing, even in these very different cutting-edge memory types. It's clearly a super versatile player in the electronics toolkit.
Absolutely fundamental.
Yeah. Okay. Now, this deep dive doesn't stop at just storing data, does it? The source has highlighted some other really intriguing applications of Fowler Nordheim tunneling.
That's right. So we've seen how crucial FN tunneling is for pushing electrons into or pulling them out of those floating gates in memory.
Right.
But now let's shift gears. What if we use that same principle to actually eject electrons completely out of a material into vacuum?
Shooting electrons out? Okay.
Right.
Where does that lead?
It leads to an area called field emission. And one source explicitly points out that field emission is fundamentally Fowler Nordheim tunneling in action.
Ah, it's the same mechanism.
Essentially, yes. You use a very sharp surface, a tip, and apply a strong electric field. Electrons tunnel right out of the material surface into the surrounding vacuum or gas.
And the sources mentioned using nanostructured tungsten oxides for this.
Exactly. Things like tungsten oxide nanowires and nanorods turn out to be really good for this.
Why them specifically?
Well, remember how tiny geometries concentrate the electric field?
Yeah, the lightning rod effect.
Yeah. Same idea here. Their tiny, pointed shapes dramatically enhance the local electric field right at the tip, making it much easier for electrons to tunnel out, even with a relatively modest overall voltage applied nearby.
So you don't need crazy high voltages across the whole setup.
Right. Plus, these nanostructures have a huge surface area relative to their volume. They can often handle surprisingly high currents without melting. And they tend to be quite stable chemically and physically.
Okay, so good properties for spitting out electrons. What kind of technologies does that enable? Using electrons fired out of these nanowires.
Think about things that need electron beams. Advanced imaging, like electron microscopy or spectroscopy techniques that analyze materials by hitting them with electrons.
Okay, scientific instruments.
Definitely. Also, things like compact X-ray generators, perhaps for medical imaging or industrial inspection, and even certain types of flat panel display devices.
Displays, how does that work?
Well, imagine tiny pixels, each made of a bunch of these nanowire tips. You apply voltage selectively to make them emit electrons, which then fly across a short gap and hit a phosphor screen, making it light up, like a microscopic CRT almost.
Yeah, a field emission display.
Exactly. The incredibly sharp tips allow emission at low voltages, as we said. Researchers reported some impressive results in the sources needing less than 1 volt per micrometer of distance to get electrons flowing.
That sounds pretty efficient.
Yeah, and achieving high current densities, too. One study mentioned getting up to 170 microamps from tungsten oxide nanowires grown on a tiny, sharpened tungsten tip. And there's active work on developing actual pixels made of these nanowires for potentially very high contrast and bright displays.
Wow, so the same basic quantum physics that lets us store our vacation photos on a flash drive could also be used to build the screen we view them on. That's a really fascinating connection.
It really shows the versatility of the underlying principle.
Okay, and there was also another really intriguing mention involving light emission, but in these incredibly thin, sort of two-dimensional materials, van der Waals materials.
Yes, this is another very promising frontier. Using these atomically thin materials, often called van der Waals or 2D materials, researchers managed to get electroluminescence.
Light from electricity.
Right, emission of light when current passes through.
Yeah.
But they did it in devices made from carefully stacked layers of different 2D materials.
Layering again.
Yes, it's all about layering these days. Specifically, one device used graphene, then hexagonal boron nitride, HBN, then molybdenum disulfide, MOS2, then more HBN, and finally more graphene.
Okay, a sandwich. Graphene, BNS, 2S2 LEBN graphene.
Exactly. Now, HBN is an insulator, MOS2 is a semiconductor that can emit light, and graphene is the conductor for the contacts.
Right.
The clever part was, this wasn't like a traditional LED that relies on PN junctions. Instead, they applied a high enough voltage across the whole stack.
Yeah.
And electrons tunneled from one graphene layer through the thin HBN barrier into the MOS2 using FN tunneling.
Tunneling through the insulator.
Yes. and simultaneously holes, the absence of electrons, funneled from the other graphene layer through the other HBN barrier into the MOS2, also via FN tunneling.
Electrons from one side, holes from the other, tunneling into the middle layer.
Precisely. And when those electrons and holes meet up in the MOS2 layer, they recombine and release their energy as photons as light.
Wow. So FN tunneling is the key to getting the charge carriers into the light-emitting layer in this exotic structure.
It is. It allows for efficient injection without needing conventional semiconductor junctions. This approach could lead to very efficient, maybe even flexible, light sources built entirely from these 2D materials. Really neat potential for future integrated optoelectronics.
So we're not just storing data or maybe making displays, but potentially even lighting up our future tech with devices based on this quantum tunneling.
That's incredible. Okay, finally, the sources mention one more area. FN tunneling is also studied in single-molecule junctions. That sounds like we're getting down to the absolute nuts and bolts.
We really are. This is pushing towards the ultimate limit of miniaturization. Scientists use these amazing techniques, often called break junction techniques.
Break junction.
Yeah, where they carefully stretch or break a tiny metal wire, creating an incredibly small gap between the two broken ends, maybe just nanometers wide or even less.
Okay, a tiny gap.
And then sometimes they can get a single molecule to bridge that gap, forming what's called a single molecule junction, just one molecule connecting the two sides.
One molecule is the entire circuit component.
Essentially, yes. And studying how electrical current flows through that single molecule is crucial for understanding fundamental charge transport and for developing future molecular electronics.
Right, building circuits from molecules, that's the dream. And Fowler Nordheim tunneling turns out to be one of the key ways electrons can travel across that molecule, especially when you apply a significant voltage bias across the junction. The molecule itself, or the gap around it, acts as the barrier.
So even at the single molecule level, FN tunneling is a relevant way for charge to move.
Absolutely. Understanding when direct tunneling dominates versus when FN tunneling takes over and how the molecule's structure influences this is really fundamental science that underpins the potential for molecular scale devices.
It's just incredible, really incredible to think that this same quantum mechanical effect, electrons sneaking through barriers thanks to strong fields, is relevant at scales all the way from macroscopic memory chip.
Billions of transistors.
Down to field emitters, these 2D light devices, and even individual molecules. It really underscores how fundamental this is.
It's woven into the fabric of modern electronics in ways most people never realize.
Okay, so to try and wrap up this deep dive into Fowler Nordheim tunneling, what's the key insight? The main thing you'd want our listener to take away from all this?
I think the main takeaway for me is that Fowler Nordheim tunneling, even though it sounds like abstract, maybe even weird quantum physics.
Definitely sounds a bit weird.
Yeah. It's actually a true workhorse. It's a practical, essential mechanism that's really powering a huge range of the modern technologies we rely on, especially as we saw in non-volatile memory, which is just foundational to our entire digital world.
Right. Can't live without memory.
Exactly.
Right.
And beyond memory, it's also proving crucial in these exciting emerging areas. Advanced displays, maybe these new 2D light emitters, perhaps even manipulating matter down at the single molecule scale eventually. It's not just historical, it's still very much driving innovation.
Absolutely. It's definitely one of those aha moments, isn't it? Where you realize how a seemingly esoteric concept from a physics class has these profound, very tangible impacts on your daily life. It really makes you wonder.
And maybe that leads to a final thought for our listeners. As scientists and engineers keep pushing, exploring new materials like those nanowires or 2D sheets, designing new device structures that leverage tunneling, what other groundbreaking innovations might be just around the corner? What could emerge from getting even better at understanding and controlling these quantum effects?
Yeah, what's the next big thing enabled by quantum mechanics? And maybe even broader, are there other seemingly fundamental physical phenomena like tunneling that might be hiding similarly transformative technological potential, just waiting for us to figure out how to unlock them?
That's the exciting part, isn't it? Always more to discover, more ways to potentially harness the fundamental laws of nature.